Here's the test. Front side, multiple choice, matching, just what you'd expect. On the bottom part of this review behind, I'm going to talk about in a little bit the terms, the concepts from the chapter. First 20 questions are like that. We'll talk about them a little bit, but mostly I'm going to spend my time on the review on the problems. The bottom, there are some problems. Back, all problems, math, and some equations. All right. So it's probably going to be about, I'd say, something like a little over half math or equation problems like these, or math problems like these, and a little over half, maybe about 60%. And the other 40% will be questions. Now, I don't have a lot of those questions and short answers and multiple choice and matching on here because you have to study those. Okay, I can't really prepare you for that without studying. Right now, if I asked you to classify something as a solution, suspension, or colloid, you probably couldn't do it. All right, if I said, what's mayonnaise? What's oil and vinegar salad dressing? What's Kool-Aid? All right, what's Jell-O? You probably couldn't tell me because you haven't looked at them over. All right, maybe you knew it two weeks ago when we first covered it, but you don't know it now. Same thing's true with endo and exothermic solutions and rate of solution and solubility rule. What is a solubility rule? The one solubility rule, like dissolves like, and can you apply it? All right. The Tyndall effect. Yeah, that's all in this chapter. A lot of times when you see these things, you forget they were in this chapter. But we did demos on them early on, and we did a lot of notes and questions. We even had worksheets. I probably had about half a dozen worksheets in this chapter on this stuff, and it was all on this chapter. Now, I can't help you, like I said, with that stuff, but I can help you with about 60% of the test, which is the math and the problems, the actual equations kind of stuff. So let's do that right now. Oops, I don't want to go there. Okay, first two. Okay. Calculating percent solution. I could ask it several ways, but the way I asked this one was given the grams of solute and the grams of solvent, can you calculate the percent solution? Here's what you should have done. You're going to need to show me the work. Percent solution equals mass of solute over mass of solution. And it's key that it's the solution, not the solvent, and then times 100. Part over the whole times 100, like we all have seen before. So it's the mass of the solute, which is 24 grams, over the mass of the solution, which is 110, right? No, it's not. It's 110 grams of water and 24 grams of solute. So 134 grams, right? Times 100. What'd you get for that? Significant figure should have 2. It's about 18%, I think. 18%. All right. Okay. All right. So there's your first one. I could have asked if this question had one word different. Look here. This is said 110 grams of solution. You would have divided by 110 down here. You only divide it by them added together because that was the solvent. Water is the solvent. All right. Let's look at the next one. Next one's a molarity problem. And this is like an apples or strawberries in a basket problem. So how do you figure? Well, 4 molar means 4 moles per liter. 4.0 molar means 4.0 moles per liter. Okay? There are 4 pounds of strawberries in every one basket. Pounds per basket. I picked 3 baskets. I could look at it common sense, like I just said, or I could look at it as a conversion problem. Either way it works and leaves me with moles if I multiply these guys out and get 12 pounds or 12 moles of strawberries. All right, that's a lot of strawberries, 12 moles of strawberries. How many is in 1 mole of strawberries? 6.022 times 10 to the 23rd. There aren't that many strawberries in the world, I don't think. That's an awful lot of strawberries. I'd have to say no. There aren't that many strawberries in the world. Anyway. Find the molarity. This time I'm giving you another molarity problem. When I'm asking you for the molarity, I'm not giving it to you. If I ask you for the molarity, you're going to have to show me the equation, like you would always on a test. So, molarity equals moles of solute per liter of solution. Not to be confused with Molarity. I know they're very similar. That's moles of solute per kilogram of solvent. We're going to do one of those in a little bit. All right, moles of solute per liter of solution. Another thing that people confuse, often smashed together, times 100. Do I multiply this by 100? This is not a percent. I don't multiply by 100. All right, I do have to get the moles correctly. I have 12.5 grams of salt, so I have to convert that to moles. Grams at the bottom, moles at the top. 1 mole contains. I add up Na and Cl, get the molar mass. It's about 58.443. That's your numerator. Denominator, 1.43 liters of solution. What do I get for that answer? I do all that. Jared, what'd you get?
0.150.
Anybody else get that? 0.150? That's molar, or moles per liter. Okay? All right. Next. And we did labs on all these too. I mean, we did labs dissolving them. We did labs with a. We're going to do a lab with a freezing point tomorrow. All right. I'm sorry, not tomorrow for you guys. In about 15 minutes. All right. We're going to be doing that soon. All right. Making ice cream. By the way, I don't think I made this clear. Let me make it clear now to you what's going on here. All right. When I talked about freezing point depression, I think it's obvious why we add salt to the road, so water won't freeze and turn into ice. Okay, but why do I want to melt ice if I'm making ice cream? Well, the answer is I don't. I don't want to melt the ice. I want to make the ice's melting point be lower. Remember this. Take a look at this. You don't need to copy this. Just watch. Remember this graph? Okay. If I don't have any salt in that water that you're about to use to make your ice cream, if I don't have any salt in there, the temperature of that ice water you're going to be mixing this stuff up in is going to be 0. 0 degrees. 0 degrees is cold, but it's not that cold. Okay? It's not really cold enough to turn your milk into ice cream. Okay? So, what do? We add salt, rock salt. That's back there. I'll show you how much to add and everything. And that lowers the freezing point to maybe about 4 degrees Celsius. That's a degree, not a 40. All right, if it's at minus 40, it's pretty cold. It's about 4 degrees Celsius, minus 4 degrees Celsius, around there. Now that's cold enough to make your ice cream turn into, well, it really won't turn as hard as like the kind you buy in a store, but it will be like a Frosty, basically, like a Wendy's or a Blizzard at where? Blizzard. Dairy Queen. So let me explain it again, one more time. Listen. Shh. The reason we're adding the salt is to lower the freezing point, because otherwise, if I just put ice water there, the temperature is only 0. But salt ice water is going to be lower than that. And so it's actually going to make that stuff freeze. Because the actual temperature of the ice cubes is below 0, but I won't know that if it's a mixture of water and ice, which it will be. All right, let's do this problem. You'll be doing another problem similar to this in a few minutes. Determine a new freezing point if I got 30 grams of salt added to 600 grams of water. And it's an ionizing solute. So I'm going to eventually have to use this equation, delta TF equals KF times M. But there's a problem with that. I don't have M. I have KF. KF will be given to you on the test. It's right up here in this corner, 1.86 degrees Celsius per mole. It'll be given to you on the test as well. But I don't know molality, so I've got to calculate the molality first. Molality is moles of solute over kilograms of solvent. How many moles of solute I have? Well, I have 30 grams of salt. I know that. 30.0 grams. Grams in the bottom, moles in the top. 1 mole contains. I use salt again, so you wouldn't have to do our molar mass, 58.443. Over, how many kilograms you have? 0.600 kilograms, because I had 600 grams. Everybody should be able to convert that in their head. 600 grams is 0.600 kilograms. And what do I get for that molality? Just that answer, just the molality. What do you get? Josh, what'd you get?
I got 0.86, but it's not right.
Why would it not be right? Significant figures, it needs one more. What do you have? 28 what? 856. Okay. 9.856 molal. Does that look good? All right, now that's the molality, but I'm not done yet. I'm nowhere near done. I got a lot more to do. I got to get the freezing point, which means I got to use this equation. Delta TF equals KF times M. My KF, I told you don't have to memorize. It's 1.86. I will give it to you on a test to degrees Celsius per mole. My molality is 0.856, you just told me. What does that give me for my change in freezing temperature? Multiply those out, what do you get, Karen?
3.18.
No, not yet. I know what you're doing. You went to, well, right now, what do you get?
1.59.
1.59 degrees Celsius. But, as she's realizing, there's still something else to do. It's an ionizing solute. Salt breaks up into Na ions, aqueous, and chloride ions, aqueous, not chlorine gas, as we know. All right, so I get 2 of these. I have to multiply that freezing point change by 2 because it's an ionizing solute, and I get 3.18 degrees Celsius. Is that correct? But that's still not the right answer. That's the delta TF. What's the new TF? Negative 3.18. That's the final answer, believe it or not. So there's a lot to do on that problem. A lot of little things you can do wrong on there. Okay? All right? Everybody good with that? All right. Now, I also have a dilution problem on here. There'll be a dilution problem on the test. You know what to do on those. M1, M1, V1, M2, V2. All right, now you have to read. These are very important you read correctly. All right? How many milliliters of this concentration are required to prepare this many milliliters of that concentration? So my initial concentration is what? 16.0 molar. My V1, it wants to know how many milliliters of that I need. That's my unknown. My M2 is what it's going to be, 0.900 molar, and I want to make 1.20 liters of that. You know, these are the kinds of dilutions I have to do all the time. All right, when I'm making up stuff for you. Now, in the last lab we did, and in some of the labs in the future we're going to do, I'm not going to have everything ready for you perfectly. So you'll have to dilute it or make it up yourself. All right, but that's the stuff I have to do whenever I'm making it. I want a 1 molar solution for this titration lab. I got to dilute it. All right, from 12 molar, which is what it comes in the bottle. All right, I've solved for V1. Here's my equation: M1 V1 equals M2 V2. I have to get M1 by himself, so V1 by himself, so I'll divide by M1. Is that correct? Divide both sides by M1. And then I get V1 equals, plugging them in here, M2 V2 over M1. M2 is 0.900 molar. V2, that's M2, right? And V2 is 1.20 liters over M1, which is 16.0 molar. That look good, everybody? Molar cancels, leaves you with liters. What do you get for your V1 in liters? Now, I know you probably changed it, but right now in liters, what do you get, Allie? Anybody? What do you have? 0.06. 0.06. 8 or 7.5? Well, I got 3 significant figures, so I'll say 7.5. Is that right? 0.0675? Now, hold on. It's not quite the end. And there's a couple other things I want to talk to you about because I may ask the question differently. Obviously, that's in liters. What will that guy be in milliliters? I could just convert it in my head, but liters to milliliters, 1 liter contains 1,000 milliliters. I get 67.5 milliliters. Okay? But hold on. That is the answer. But the question could have asked you, and how do you prepare that? And if you were asked, for example, how much water would you need to make this? Would it be 1.20 liters of water? No. You'd have to add that 67.5 milliliters into 1 point whatever, subtracting the 60, because this is 1,200 milliliters, so it'd be 1,132.5, right? Is that right? Milliliters of water, right? And by the way, you always would add acid to water. Okay, you should never say, "Oh, I'll put that in first, and then I'll pour the water on top of it," because it will spatter up. I think we had that. Did we watch the video on acids yet? Oh, well, that's right. We have the next chapter's on acids. We're going to be talking about that. That's our next chapter. We'll be seeing that video at the time. All right, and it shows you what happens if you do that. Okay, let's look at somebody. I've already talked about the stuff at the bottom. I'm not going to go back to that again. You need to read and study solutes, solvents, colloids, solutions, suspensions, all that stuff. But here's something I do want to point out to you, a couple of things. One is strong, weak, and non-electrolytes. You may think, what am I supposed to just memorize notes on this? Not really. How do I know barium carbonate is a non-electrolyte?
It doesn't dissolve.
Because it doesn't dissolve. Since if I look him up on that same sheet I got to use later on anyway, if he doesn't dissolve, he's not an electrolyte. Silver nitrate is an ionic compound on that sheet, and he does dissolve, so I would call him a strong electrolyte. Now, there are some you do have to just kind of know, all right? And those are right here. Sugar is one of them. He is a non-electrolyte even though he does dissolve because he doesn't break up into ions. Vinegar is a weak electrolyte along with one other guy you should know. That's a weak electrolyte. Anybody that has citric acid in it, like lemon juice, orange juice, pineapple juice, any kind of citric acid is going to conduct a weak current. And vinegar. All right? And bacon. Not bacon. All right.
What about bacon?
Bacon. Let's do these two on a separate board here, and let me say a few words about them before I start them. How much time we got? About 5 minutes. All right, listen. These are opposite, and a lot of times they cause confusion. In this case, what I'm asking you to write down the dissociation equation of what happens when magnesium chlorate dissolves in water. You need to look him up and see if he has a big S next to him. If he does, yes.
Will there be an H2O over the line?
No, not necessarily. All right, I'll just say it's a dissociation equation. I mean, there could be one over the line, or probably not because it's hard for me to write those. It doesn't matter.
Okay.
This is we are not doing chemical equation. It will clearly say that it's a dissociation equation, not a chemical decomposition. That will be a totally different thing, and we're not learning about those in this chapter. I'm not going to ask you any chemical decomposition. That's not the part that I was telling you would be confusing. Here's the confusing part. I looked this one up, the ones where they're just dissolving, and I see if they're soluble. If they're soluble, they work. In this case, I look up what's made from these two guys, and if they're insoluble, they work. If this guy I look up and he has a big I next to him, or a P, or an A, I put it cross, I put an X. Nothing happens. If I look this guy up and both of them are soluble on the other side, calcium nitrate and silver chloride are both soluble, I put an X. So it's the exact opposite. Okay? Here I'm looking for the precipitate. That means the guy that's insoluble. Here I'm looking to see if he dissolves. That means he has to be soluble. All right, let's show you what a very bad answer would look like for this guy. Magnesium plus chlorate, MgClO3 yields Mg plus ClO3. Now that's a terrible answer. I haven't done anything that I asked you to do. I did not, in the first case, write down little AQs next to the words. That means they've dissolved in water. I did not bother to look up the charges of magnesium and chlorate and write them down. +2, -1, MgClO3, 2. You don't do that, can't get it right. Every time I write magnesium chlorate, since the time I taught you back in probably September or October, you had to write it correctly. I also did not write little AQs here. I did not write the charges up here. That's +2 and a -1. And I did not balance it with the 2 there. That is the correct answer. You have to do all of those things to get full points. Everything you don't do, you get 1 point off. Forget these 1 point, forget charge 1 point, forget a balance 1 point, don't write it correctly. All right, all of that stuff. All right, now this next one, same basic idea. I have to write it correctly, but also predict the precipitate. So AgNO3, I'm going to do this very quickly because we're almost out of time, plus CaCl plus 2 -1 CaCl2 aqueous yields CaNO3 2 plus AgCl. That guy, I look him up, and this is another weird part. I look up AgCl, and he says insoluble. In other words, he doesn't have an S. But I put an S there, because that S there means what? Does it mean soluble? It means solid. It means it fell to the bottom of the beaker. I put that big arrow there, too. I balanced this guy with a 2 there and a 2 there. And I put little AQ next to this guy here. Oh, by the way, I did not put the rest of the words in there, but the words are implied. Yeah.
Do you have a copy of that quiz so I make sure I do the same type of